Welcome to Biogas Basics. My name is Jürgen Kube, and today I will talk about a reactor form that occasionally pops up in the AD world, the plug flow reactor. I will explain the concept, theoretical advantages and major challenges. Most commercial AD plants do not use plug flow technology, and I hope that by the end of my presentation you understand why. Let's start with the definition of a plug flow reactor. A flow reactor is characterized by a concentration gradient of the reactants between the entry and the exit point. A plug flow reactor is a special type of flow reactor in which fluid elements form a plug and travel uniformly through the reactor. All fluid elements have the same residence time and travel with the same axial velocity. The reactor has a spatial axis. The entry and exit points are usually at opposing ends of the reactor. The alternative to a plug flow reactor is a continuous stirred tank reactor, or CSTR. The CSTR is characterized by the absence of a reactant gradient. Feedstock that is added to a CSTR is immediately diluted to the outlet concentration. In a CSTR, not all fluid elements have the same residence time. Instead, there is a residence time distribution. Different substrate particles leave the reactor after different residence times. After adding fresh feed, some fluid elements of the feed immediately leave the reactor, whereas other fluid elements stay in the digester forever. Let's briefly talk about residence time distributions. The residence time distribution is an important characteristic of a reactor. It shows what percentage of fluid elements have which residence time. The residence time distribution function is labeled E of t and has the unit time to the power of -1. The area under the E of t curve is 1. The integral of the residence time distribution function is the cumulative residence time distribution function f of t. It describes the percentage of fluid elements that have already left the reactor at time t. It approaches 1 when t goes to infinity. The hydraulic residence time is the average time a fluid element spends in the reactor before it exits. The residence time distribution function, E of t, of an ideal plug flow reactor is the Dirac function delayed by the hydraulic residence time. It is shown below. A Dirac pulse is an infinitesimal short pulse of infinite height. All particles exit the ideal plug flow reactor at once after the hydraulic residence time. The cumulative residence time function is the Heaviside step function. Up to the hydraulic residence time, none of the particles have left the reactor. After the hydraulic residence time, all particles have left the reactor. When a tracer is injected into the feed as a single pulse at t equals 0, E of t is proportional to the tracer concentration in the outlet at time t, and f of t is the percentage of tracer that has left the reactor up to the time t. Why is the plug flow reactor better than a CSTR in theory? The concept of the plug flow reactor is that the substrate travels through the reactor in the fluid element that has no inflows and no outflows other than biogas. Thus, the plug flow reactor can be seen as a batch reactor that travels along the reactor axis. At the beginning of the batch process, the substrate concentration is high. The substrate depletes as the reaction progresses, and the reaction rate, which is proportional to the substrate concentration, slows down. At the end of the batch, or at the outlet of the plug flow reactor, after all, a plug flow reactor is a batch reactor where the time axis has been exchanged for a spatial axis. The substrate concentration and the reaction rate are low, lower than that of a gradient-free continuous reactor of the same size. Therefore, the plug flow reactor is more efficient than a continuous reactor regarding substrate conversion. However, it must be able to maintain its substrate gradient. The formulae for the batch and plug flow reactor are shown on the screen. Starting with the first-order reaction, we integrate the equation, insert the initial condition, and solve for the substrate concentration. We get the typical exponential decay for a first-order batch reactor. With the coordinate transformation, we can get the spatial substrate profile for a plug flow reactor. Compare this to a continuous perfectly mixed system, or CSTR, at steady state with the same first-order reaction. Solving the equation gives the hyperbolical relationship between hydraulic residence time and substrate in the reactor and its effluent. We can plot the substrate concentration along the reactor axis for the plug flow reactor and the CSTR. The substrate gradient in the plug flow reactor is the characteristic first-order exponential decay profile. It has high concentrations at the inlet. The concentration at the inlet is the feedstock concentration, and low substrate concentrations at the outlet. The substrate gradient is the defining feature of a flow reactor. On the other hand, the CSTR is gradient-free. It has the same concentration everywhere in the reactor and in the outlet. On average, the concentration is lower in the CSTR than in the plug flow reactor, so the reaction rate and the substrate conversion are lower as well. That is why the plug flow reactor has a higher conversion efficacy than a CSTR with similar residence time. I have written a short computer program to visualize the impact of various reaction parameters on the steady-state performance and residence time distribution functions of a flow reactor with a first-order reaction. The balance equation is shown on the right. The change of substrate concentration over time, ds by dt, depends on two terms, convection and reaction. The first term, minus u ds by dx, describes how substrate is transported through the reactor with the velocity u. The second term, minus ks, is conversion of substrate to biogas with a first-order reaction. The figure comprises three subfigures. The top graph shows the substrate concentration along the dimensionless reactor axis for a steady state. The plug flow reactor is shown as a bold line. At the inlet, the concentration is 100%, and along the axis is an exponential decay. The conversion is almost complete. The outlet substrate concentration is only 1.8% here. As a comparison, I have shown the substrate profile of a CSTR of equal size as a dotted line. The CSTR is gradient-free. Here it converts 80% of the substrate. We see that the plug flow reactor is much more efficient than the CSTR in converting substrate to biogas, but it also has much higher substrate concentrations at the inlet of the reactor. The middle graph is the residence time distribution function E of t. For the plug flow reactor in bold, it is a Dirac impulse at 20 days, the residence time in this example here. A Dirac pulse has infinite height, but the ordinate is curtailed here. The residence time distribution of a CSTR is an exponential decay function, here shown as dotted line. This means that after adding substrate marked with a tracer to the digester, some of these marked substrate particles will be immediately flushed from the reactor and the amount of marked particles in the effluent, equivalent to the concentration of the tracer, will decay exponentially. The last figure below is the cumulative residence time distribution function f of t. For the plug flow reactor in bold, it is a Heaviside function at the residence time. For a plug flow reactor before the residence time, none of the fluid elements have left the reactor, and after the residence time all the fluid elements have left the reactor. For a CSTR, the cumulative distribution function is 1 minus an exponential decay function, here shown as a dotted line. Now let's see what happens when we vary the reaction constant. First, we increase the reaction constant from k equals 0.2 days to the power of minus 1. We see that the substrate gradient becomes steeper as the substrate degrades quicker. In the CSTR, the substrate concentration everywhere in the reactor decreases with higher reaction constants. Similarly, when we lower the reaction constant, the gradient in the plug flow reactor flattens, and the concentration in the CSTR becomes higher. If we set the reaction constant to 0, no reaction takes place and the substrate concentration everywhere in the reactor is 100%. Note that regardless of the reaction constant, the outlet concentration of the CSTR is always above the outlet concentration of the plug flow reactor. The residence time distribution functions are independent of the reaction constant. In fact, they are independent of the reaction. The distribution functions can be calculated and measured in a reactor without reactions by adding inert traces to the feed. The first reason why plug flow reactors are not a thing in AD is the inoculation requirement. Remember, feedstock does not spontaneously convert into biogas. The AD process requires the presence of microorganisms, fermentative, acidogenic, and methanogenic microorganisms. In a reactor without inoculation, the microorganisms would need to grow in the feedstock as it travels along the digester axis. Some feedstocks, like energy crop silages, have such a low pH that no growth would be possible. Even if the feedstock is pH neutral and contains all required microorganisms of the AD process, the microorganisms would still need to grow while the fluid element travels through the reactor. At the inlet of the reactor, where the substrate concentration is the highest, and the reaction rate should be the highest as well, the microbial biomass concentration would be the lowest. In the first part of the plug flow reactor, very little would happen. The maximal biomass concentration would be at the end of the reactor. Also, fermentative bacteria would outgrow acidogenic and methanogenic microorganisms, and the reactor would acidify. This is what happens when crops are ensiled. The acidogenic bacteria outgrow acidogens and methanogens, and the pH quickly drops, so their growth is inhibited. And eventually, even the fermentative bacteria are acid inhibited, and the silo stock is stable and can be stored. A silo is a batch reactor, but we learned already that batch reactors and plug flow reactors have similar properties. So we need inoculation. But how much and where does the inoculation come from? It will come from the end of the reactor. At the end of the reactor, the substrate concentration is at the lowest and the highest biomass concentration has been achieved. We describe the inoculation or recirculation with the recirculation factor R. R is the ratio of the recirculation stream to the feed stream. When recirculating effluent to the inflow of the reactor, the velocity in the reactor increases by the factor 1 plus R. For batch reactors, there are some guidelines for the inoculation requirement. In the GB21 method, the organic dry matter ratio of inoculum to feedstock is 1:1. The VDI 4631 recommends an organic dry matter ratio of 2:1, i.e. 2 parts inoculum to 1 part of feedstock. If the inoculum has 5% volatile solids and the feedstock has 30% VS, 12 parts of inoculum must be mixed with 1 part of feedstock to ensure an undisturbed conversion and prevent acidification. If we follow the GB21 method, the ratio is still 6:1. In reality, inoculation streams are usually 3:1 and can go down to 1:1 in some plug flow reactors that can handle very high viscosities. We will talk about viscosities and mixing in a minute. Let's go back to our experiment. A plug flow reactor with 20 days hydraulic residence time and a reaction constant of 0.2 days to the power of -1. We can now examine what happens if we introduce recirculation. Let's start with a recirculation ration of R equals 1. For every ton of feedstock fed, 1 ton of recirculate is added as inoculum to the digester, and in total, 2 tons are traveling through the digester. Upon reaching the end of the digester, 1 of the 2 tons are sent back to the inlet of the reactor and 1 ton will be discharged. Suddenly, for half of the feedstock particles, the hydraulic residence time drops from 20 to 10 days. The other half will go back to the inlet and travel through the reactor again. 10 days later, the particles will appear at the outlet again, upon which half of the half, a quarter, will be discharged. The other quarter will be pumped to the inlet again and reappear at the outlet after 30 days. At which point, 1/8 stays in the reactor. After 40 days, it is 1/16. After 50 days, 1/32, and so on. The average hydraulic residence time is still 20 days, but some particles leave before the average residence time, while others will spend longer in the reactor. In the substrate profile, we see that when recirculation is added, the inlet substrate concentration drops. It almost halves when R equals 1. Also, the outlet concentration increases. In short, recirculation starts to flatten the substrate profile. The reactor benefits from lower substrate concentrations at the inlet, but that also leads to a slower gas production rate and more undigested substrate leaves with the effluent. In the residence time distribution, multiple Dirac impulses occur. Each of them is of infinite height, but the height of the impulses decreases over time. Here, I have normalized the impulse so we can see the effect. The cumulative residence time distribution function comprises multiple steps. Let's compare it again to the case with no recirculation, which shows the undiluted substrate gradient and the single Dirac impulse and Heaviside function at the residence time of 20 days. We can now increase the recirculation rate. The higher the recirculation rate, the faster the fluid elements travel through the reactor and the more the substrate will be diluted at the inlet of the reactor. As we increase the recirculation rate from 1 to 2 to 3 to 4 to 8 to 16 and finally to 20, both the substrate profile and the residence time distributions approach the CSTR behavior. The second reason why it is de facto impossible to build a plug flow reactor in AD is axial dispersion. What is axial dispersion? Dispersion is mass transport due to concentration gradients amplified by mixing and velocity gradients usually generated from external energy input. Dispersion is similar to diffusion, but diffusion relies only on random molecular movement and is generated without external energy input. Both effects can be described with Fick's laws. In AD reactors, the dispersion coefficient is much higher than the diffusion coefficient. Dispersion can originate from velocity gradients. Remember, the plug in plug flow reactor means that every fluid element travels through the reactor with the same velocity, arc as plug. Along the section of the reactor is perfectly radially mixed with no radial gradients, while at the same time no axial mixing occurs, and a perfect axial gradient is visible. There are 2 ways to achieve a plug flow. The first one is turbulent flow. This is characterized by a small laminar boundary layer and a large bulk of the fluid with intense radial movement and uniform axial velocity. Classical plug flow reactors in chemical reaction engineering are operated that way. The second way is laminar flow of a fluid with a yield stress, for example a Bingham-fluid. But this is only a theoretical case. I will briefly discuss laminar Bingham fluids later. Ideally, a plug flow AD reactor would operate under these conditions, either turbulent flow or the flow of a Bingham-plastic. Only the former offers perfect radial mixing. The latter has no radial mixing. turbulent and laminar flow can be differentiated based on the Reynolds number. It is characteristic length times velocity times density divided by dynamic viscosity. If we just look at orders of magnitudes here, the characteristic length is the diameter or wetted perimeter of the reactor and is around 10 meters. The velocity is around 1 meter per day, and for the density and viscosity we take the properties of water, 1000 kilogram per cubic meter and 1 millipascal second. If the reactor is filled with water, the Reynolds number is 100. The transition from laminar to turbulent is at Reynolds numbers over 2000. In reality, the viscosity of digestate is higher than that of water, so the Reynolds number is even lower. AD plug flow reactors will always be laminar. The formula shown here is for a Newtonian fluid. For power law and Bingham fluids it becomes more complicated, but the flow will still be laminar. Why is this important? A developed laminar flow is characterized by a parabolic flow profile. The velocity is zero at the wall, while in the middle of a circular pipe or at the top of an open channel flow, the peak velocity is twice the average velocity. Fluid elements travel with different velocities through the reactor and there is no longer a plug. I have visualized the flow profile of a Newtonian fluid in a laminar open channel flow by solving the Poisson-equation here. The boundary conditions are the no-slip condition at the wall. That means the velocity is 0 at y equals 0, x equals 0, and x equals 1. The boundary condition at the surface of the channel is the no-stress condition. The first derivative of the velocity in respect to the y-coordinate is 0. On the abscissa, we have the velocity of a developed laminar flow normalized to its average velocity. The ordinate shows the y-coordinate or the dimensionless height of the channel. We are looking at the flow profile from the side of the reactor. The full profile becomes visible in the 3D projection. From the top, we can see the parabolic profile. The highest velocity is on the top of the channel in the middle of the flow, the furthest away from the walls. Every flow reactor in AD has laminar flow conditions, and a laminar flow would develop a parabolic flow profile where the fastest fluid elements travel through the reactor with twice the average velocity. This means that one of the requirements of the plug flow reactor, the uniform axial velocity, cannot be achieved. In AD, the plug flow reactor is impossible to achieve. It is merely a flow reactor. At this point, I should mention that technically there is another way to generate a plug flow. A medium of high viscosity and a noticeable shear stress, for example a Bingham-plastic, will form a plug flow in an open channel or a pipe. At high viscosities, these media form a solid plug in the middle of the flow. Here the shear is below the yield stress of the fluid, and the fluid behaves like a solid. Unlike the turbulent plug flow, the Bingham-plastic flow is not characterized by perfect radial mixing. In fact, the core has no radial mixing at all as it is solid. Between the edge of the core and the wall, the shear is high enough to fluidize the medium. It effectively acts as a lubricant. I will talk more about Bingham fluids and where they appear in AD in the mixing and rheology presentation. For now, we can state that this flow condition would be disadvantageous for a flow reactor. For example, the produced biogas would not be able to leave the solid core. Strong mixing would be required to degas the digestate, and that would induce axial dispersion. Let's examine the impact of axial dispersion on the performance of the flow reactor. We need to extend the balance equation by the dispersion term d times the second derivative of s in respect to x. D is the axial dispersion coefficient. It has the unit length squared over time, for example square meter per day. The term originates in Fick's second law. It describes the flux of substrate due to dispersion. The flux J of x is defined by Fick's first law. For those interested in the maths, I have attached how to arrive at the equation at the end of the lecture. We start again with the plug flow reactor with a residence time of 20 days and a first order reaction with a reaction constant of K equals 0.2 d to the power of -1. The residence time distribution function E of t shows a Dirac impulse at the residence time of 20 days. F of t shows the Heaviside step function. For the plug flow reactor, the axial dispersion coefficient d is 0. Now we slowly increase the dispersion coefficient. At d equals 0.5 square meter per day, the Dirac impulse becomes something like a normal distribution. The cumulative residence time distribution function also softens from the sharp Heaviside function to an S-shaped curve. The circle in the substrate profile at the inlet of the reactor indicates the inlet concentration, which is the feed concentration here as there is no recirculation. As the dispersion coefficient increases, there is a noticeable jump from the inlet concentration to the concentration at x equals 0.0. This behavior can also be observed in a CSTR. The jump in concentration occurs because some of the substrate is transported downstream by dispersion. As we increase the dispersion coefficient, the residence time distribution function becomes wider and it starts to become skewed to the right. The substrate concentration at the inlet decreases while the concentration at the outlet of the reactor increases, meaning that the reactor becomes less effective in converting substrate. We can compare it again with the plug flow reactor with no dispersion. The axial dispersion leads to some fluid elements traveling faster through the reactor than others. This effect is a consequence of laminar flow, but it can also be caused by local mixing that accelerates fluid elements either upstream or downstream. We can describe the performance of the reactor as a function of the dispersion coefficient, but how to estimate the dispersion coefficient of an AD reactor? To quantify the axial dispersion coefficient, we model the flow reactor as a series of infinitely small CSTR. The concentration of a reactant C is C1 in the first CSTR, C2 in the second CSTR, and C3 in the third CSTR. In a plug flow reactor, the transport is UC1 from section 1 to 2 and UC2 from section 2 to 3. We ignore the reaction here. Now we assume that superimposed on the directed flow, U is another flow, V. Half of this flow flows upstream and the other half flows downstream. Because material cannot accumulate upstream or downstream, a flow of similar size must flow from upstream and downstream back into the section. The flows in both directions cancel each other out, but they move some of the reactant upstream and some of it faster downstream. The effect is similar to a random walk. The balance equation for the second section is dC2 over dt equals U plus 1/2 V times C1 minus U plus V times C2 plus 1/2 V times C3. Now let's model the same system, but instead of the forced random walk, we use Fick's law to describe the transport due to the concentration gradient. The transport term from section 1 to section 2 is d divided by delta x times C1 minus C2. Delta x is the distance between the sections. The dispersive transport from section 2 to section 3 is d divided by delta x times C2 minus C3. The balance for C2 is U plus d by delta x times C1 minus U plus 2 times d over delta x times C2 plus d over delta x times C3. Comparing the factors in front of C1, C2, and C3, we get the following equation. The dispersion coefficient is 1/2 of V times delta x. We still don't know the velocity V that is induced by mixing, but with the help of some simple geometry, we can deduct that the ratio of velocity V and delta x is the ratio of the volume flow induced by mixing divided by the reactor volume. For example, for a gas mixing system, this is the gas volume flow divided by the reactor volume or the aeration rate. As the gas bubbles are introduced into the reactor, they displace volume both upstream and downstream, and when the gas bubble has traveled to the surface of the reactor and leaves the liquid, the volume of the gas bubble flows back from upstream and downstream. Finally, the axial dispersion coefficient can be written as mixing volume flow divided by reactor volume times delta x squared divided by 2. Delta x is the length in the plug flow of one perfectly mixed element. Let's look at two examples. Example 1 is gas mixing. We select a volume-specific mixing energy, also called volume dissipated power, to 5 watts per cubic meter. I will talk more about reactor mixing in the digester mixing presentation. The blower for gas mixing has to work against a static pressure of 0.8 bar. We can calculate the energy demand of a blower that compresses gas to 0.8 bar in kilowatt hours per cubic meter, and divide it by the volume dissipated power of 5 watts per cubic meter. In our case, the ratio is 0.24 cubic meter gas per cubic meter reactor volume and hour of 5.76 day to the power of -1. This is our aeration rate A. The characteristic length is the distance between the gas mixing nozzles, for example 2 meters. The dispersion coefficient is 11.5 square meter per day. In the second example, we assume a horizontal reactor with a cross-section of 8 meter times 8 meter, which is stirred with one long axial mixer which has pedals each 2.5 meter. The pedal arm length is 3 meters. The pedal area is 0.5 times 0.5 meter. It rotates once per minute. The pedal displaces a rectangular torus. The displaced volume can be simplified to pi times r squared times section area of the pedal times 1 rpm. The displaced volume is 6,700 cubic meters per day. Most of the volume will be displaced axially, especially when the single pedal works together with other pedals that are upstream and downstream and are phase shifted around the stirrer axis. Tangential and radial mixing are negligible. The volume of a reactor element that is mixed by one pedal is 2.5 meter times 8 meter times 8 meter or 160 cubic meter. The volume exchange rate is 6,700 cubic meters per day divided by 160 cubic meters, or 42 days to the power of -1. The dispersion coefficient is 42 days to the power of -1 times 2.5 meters squared divided by 2, equals 132 square meter per day. If we want to do the calculation with a propeller-type mixer, we need the pumping capacity of the propeller mixer. Competent mixer manufacturers will know this number. If a mixer manufacturer doesn't know the pumping capacity of its mixer, it's a red flag. Propeller mixers are usually better suited for low viscosity systems, but the viscosity has an impact on the dispersion coefficient. The lower the viscosity, the higher the dispersion coefficient. Typically, flow reactors are designed for high viscosity applications. Low viscosity flow reactors are usually gradient-free and thus just CSTRs. These estimated dispersion coefficients are quite large. As a comparison, the diffusion coefficient of water in water is 2 times 10 to the power of -4 square meter per day. The mixer-induced mass transport is almost 6 orders of magnitudes higher. Now let's look at the combined effect of recirculation and axial dispersion. First, we set the recirculation ratio to 3. The residence time is still 20 days, but now 1 ton of substrate is diluted with 3 tons of recirculate. It takes 5 days for the feedstock plug to cross the reactor. We see Dirac impulses every 5 days. Then we introduce the effect of axial dispersion by increasing the axial dispersion coefficient from 0.5 to 200 square meter per day. The Dirac impulses gradually evolve into a smoother bell-like shape as the dispersion coefficient becomes larger. And as we increase the recirculation ratio to 8, the flow reactor behaves almost like a CSTR. The steady-state substrate profile is almost flat. The reactor is virtually gradient-free. The residence time distribution curves look like their CSTR equivalents. Recirculation is required for inoculation and dilution purposes. If we consider the effects of dispersion and recirculation on the plug flow reactor, it becomes evident that a plug flow reactor in AD, and the plug is in air quotes, has the same performance as a CSTR, albeit it is much more expensive to build and more difficult to mix. Now, does this mean we cannot use the benefits of a plug flow reactor in AD? And the answer is a qualified no. Let's go back to the ideal plug flow reactor and its substrate profile. It has no recirculation, so this profile is only academic. Without inoculation, the biogas reaction would not even start. Now let's split the reactor into several compartments. Each compartment is a CSTR, ideally mixed. We make the first compartment a bit larger. Have a look at the substrate profile. The first CSTR shows only a partial conversion, and there is a significant concentration of undigested substrate in the effluent of the first CSTR. This partially undigested substrate stream enters the second CSTR compartment. From there it goes to the third compartment and to the fourth before it leaves the reactors. Each compartment sees a reduction in the substrate concentration. The overall performance is not as good as the ideal plug flow, but it is better than that of a single-stage CSTR. And keep in mind that the ideal plug flow without recirculation is only academic. I made the first compartment larger than the others. This has 2 reasons. Reason number 1 is to lower the average substrate concentration in the system. While the CSTR-cascade does not show the substrate conversion performance of an ideal plug flow reactor, it also does not show the high substrate concentrations at the beginning of the plug flow reactor. In a theoretical first-order reaction approach, the high substrate concentration would generate a high reaction rate, but in the reality of a biogas reactor, the high substrate concentration would lead to acidification. Also, high substrate concentration would mean high viscosities and high concentration of undigested dry matter. So lower substrate concentration can be beneficial to the overall process. The second reason for the larger first compartment is the inoculum requirement. The first CSTR does not have an inoculum stream. Instead, the residence time must be high enough so that the microorganisms of the AD process do not get flushed from the system. I will talk more about washout points and growth rates in the microbial growth presentation. A certain residence time is required to ensure that the microorganisms can grow in a stable environment and do not get flushed from the reactor at the first process disturbance. All downstream reactors will be inoculated from the primary reactor. They do not require a minimum residence time to establish a stable biocenosis, as long as the fermentation conditions, especially temperature, do not change too much. The second method is to combine a CSTR with a flow reactor. This combines the benefits of the CSTR, such as low substrate concentrations and no inoculation requirement, with the benefits of a flow reactor such as high conversion efficacy. The post-digester flow reactor will be inoculated from the CSTR and does not need an external inoculation stream. The viscosity at the inlet is also much lower and the feedstock is far more homogeneous. The flow reactor has to cope with much reduced substrate concentrations and viscosities. The combined system has a high conversion efficiency while it avoids the high substrate concentration of an ideal plug flow reactor. So does this mean that a flow reactor will not work in AD? Not necessarily, but the conversion performance will be similar of that of a CSTR, which is cheaper to build and operate than a flow reactor. There is a niche application for flow reactors in AD in thermophilic biowaste fermentation. If the reactor can limit recirculation and axial dispersion, the flow reactor can ensure a guaranteed minimum residence time that is required to pasteurize the biowaste under thermophilic conditions. The minimum residence time must be proven with tracer studies. These biowaste fermentations often use structural material like straw, hay, or green cuttings to stabilize the flow in the digester and limit axial dispersion. At the high TS concentrations in these flow reactors, the digestate is likely to show a yield stress, and the flow could in theory form a rigid plug. But mixing is required to degas the fluid, and that will introduce axial dispersion. But just because up till now no plug flow systems are on the market that actually offer improved conversion efficacy to a CSTR-cascade, doesn't mean that these systems cannot be invented in the future. So, if there is a new flow reactor concept on the market, how can one assess its credibility and effectiveness? A new flow reactor concept must prove how it deals with the inoculation requirement. The inoculation stream should be clearly stated in the bidding process or conceptual design of the plant. Watch out for phrases like "we will determine this during detail engineering," or even worse, during the commissioning phase. That's a red flag. The next question is, how does the flow reactor deal with high substrate concentration at the inlet? Does it have special mixing systems in place to deal with high viscosities at the inlet? Or does it premix the feedstock with digestate, and if so, where does the digestate come from? Remember, a low viscosity in the digester might be helpful while dealing with high substrate concentrations at the inlet, but low viscosities will also promote axial dispersion, and the viscosity will decrease along the fermenter axis as substrate is converted into biogas. How does the reactor limit axial dispersion? How does the mixing system look like? Does it have special forms to reduce the induced volume flow of the mixes? Look for slow-moving large surfaces and high viscosities to minimize axial dispersion, maybe a screw along the reactor axis. Lastly, how does the reactor retain a gradient? Are there special measures in place to do that? If a pilot plant or reference plant exists, visit the plant and take samples along the reactor axis. Measure TS, VS, COD, VFAs, biogas potential, or any other property. Is there a measurable gradient, or are all samples the same? If this is the case, the flow reactor is not a flow reactor, but just a fancy CSTR. Let's recap. An ideal plug flow reactor has a higher conversion efficacy than a CSTR of similar size. However, inoculation and dilution require recirculation, which reduce the efficacy of the plug flow reactor substantially. Furthermore, it is impossible to operate an actual plug flow reactor. The requirements for a plug are that all fluid elements travel through the reactor with the same axial velocity, but the flow conditions in a flow reactor in the AD industry are laminar, and laminar flows are characterized by a parabolic radial flow profile. The maximal speed of a fully developed flow profile is twice the average speed. It is impossible to maintain a plug. We should really call them flow reactors and not plug flow reactors. Additionally, mixing induces axial dispersion. The combination of recirculation and axial dispersion spread the residence time distributions. Instead of all feedstock particles spending the same time in the reactor, some particles will leave the reactor much earlier and others much later than the hydraulic residence time. The combined effects also greatly flatten the substrate profile, so the flow reactor behaves more like a CSTR than a plug flow reactor. It is usually cheaper to build and operate a CSTR-cascade with larger or more primary digesters in parallel and post-digesters in series. This emulates the substrate profile of a plug flow reactor while negating high substrate concentrations at the inlet and the requirement for an inoculation stream. If a new plug flow reactor concept emerges, can it maintain a substrate gradient? If not, it's just an expensive CSTR. If you're interested in the mechanics of a plug flow reactor, despite of what I just told you, this slide shows the Taylor-linearisation. I will not go through the formula in detail, just stop the video for details. and if you want to replicate the substrate gradient and residence time distribution calculations. The formulas are shown here. This concludes the presentation about plug flow reactors and their challenges in the AD industry. I hope you enjoyed the presentation and learned something new. And if you are an investor thinking about funding a plug flow reactor project, feel free to send 0.1% of the money you didn't lose my way. I'll see you in the next presentation of Biogas Basics.